Welcome back to another Marcus Maths video. Today we have the culmination of Unit 3 for our AP Calculus BC study. Sorry for the minimal break over the weekend. I had to sort out some last minute things, but I'll be back for this week. We have some great videos to get to. We're going to be starting Unit 4 soon, which really just moves to our applications of derivatives now that we've been doing a lot of the more complex solving. But let's get into this complex solving. We can see this first question has a second derivative. Let's go ahead and get started. If you haven't already, make sure to like and subscribe to the YouTube channel as we continue with this prep. But let's take a look. This first question has a quotient right here. We have 10 over 3x to the power of 3, but it's not really a quotient when you realize that we really just have 10 over 3 x to the power of negative 3 like this, and that way we can actually differentiate a lot easier. Notice this 10 over 3 is not even going to get differentiated because it is a constant multiple. So when we do the first derivative, we're just going to do 10 over 3 negative 3, so negative 3 times 10 over 3 x to the power of negative 4, and then when we do the derivative a second time, we're just going to multiply negative 4, so now we have negative 4 times negative 3 times 10 over 3 times x to the power of negative 5. Now we can simplify. Negative 4 times negative 3 times 10 is 120, divided by 3 is 40, and then we just have 40 times x to the power of negative 5. We just move our x to the power of negative 5 to the denominator to turn the exponent positive, and we're left with 40 over x to the power of 5. And this is indeed our second derivative. Okay, on to our next question. What sequence of rules can be used to differentiate h in its current form? We can see we have the outer function of the to the power of 2. That's what we're going to do first. So first we're going to do a chain rule, because we're going to differentiate the outer function, and then we're going to differentiate the inner secant function. But then notice, for the secant function, we have another inner function, which is our 4x, which we're going to have to differentiate afterwards. So we're going to actually have to do two chain rules here. Chain rule, then chain rule again, because we have two sets of outer functions and inner functions. So C is the correct answer here. Okay, moving on to the next, we're going to use implicit differentiation here. Remember, implicit differentiation, we have to get our variables by themselves on one side, which we already have. It's really nice here, so we're just going to differentiate. Whenever you differentiate a y, you have to include dy over dx right next to it. So let's start off with this first part, x to the power of 3y. We're going to use the product rule here. So we can take the derivative of the first term, of the first function that's multiplying, and we get 3x to the power of 2. And that is times the regular function. Then we add the regular function for the first one times derivative of the second. Derivative of y is 1. But remember, whenever you take the derivative of y, we include dy over dx. Now we are going to differentiate our next term, which is negative 2x to the power of 2. We get negative 4x. Then we differentiate the last term. We get 4y to the power of 3. Whenever you differentiate a y, always include that dy over dx. And then the derivative of any constant is equal to 0. So now we have 0 on that right side. From here, our next step is to get our dy over dx's by themselves. So let's move over the two other terms first. On the right side, we're going to have negative 3x squared y plus 4x. And then our left side is going to be our two terms with a dy over dx is x to the power of 3 dy over dx. And then we have plus 4y to the power of 3 dy over dx. Now we're just going to factor out our dy over dx from each term. Now we have dy over dx times x plus 3 plus 4y to the power of 3. And then we're just going to divide both sides by this parentheses. So that means we have negative 3x squared y plus 4x over x to the power of 3 plus 4y to the power of 3. And we can see the only matching answer with this expression for dy over dx is answer choice C. That they just move around the two terms in numerator, which maintains equivalency. Okay, on to the next. We're going to use chain rule here because we can see we're taking the derivative of an outer function and an inner function. Remember how this works. Take derivative of the outer, keep the inner function the same, and then we multiply by the derivative of the inner function. All right, so how this is going to work, we're just going to replace all the x's with 4s. Let's go ahead and do that. So now we're going to do h to the power 4 and the derivative of h. Well, not h to the power 4, h of 4 and the derivative of h of 4. Derivative of h of 4 is 1, so we're going to multiply 1. That's going to do nothing, so we can eliminate this term. H of 4 is equal to negative 2. And then we take the derivative of f at negative 2, which is 28. So that means our answer, the derivative of h at 4 is simply equal to 28. Okay, on to the next. We're given the first derivative and we're trying to find the second derivative. Now that we know the first derivative is this, we can just differentiate. Okay, remember we're doing product rule here, and whenever you differentiate the y, always include dy over dx. So we're going to take derivative of the first function, which is 6x times second function, and then plus first function regular 3x squared, and then derivative of the second function, which is dy over dx. But then remember, we know what dy over dx already is, so we're going to substitute out dy over dx with times 3x squared y. And then we can combine like terms here. 3x squared times 3x squared is 9x to the power 4 y, and then plus 6xy. And this is our second derivative here. Okay, so 6xy plus 9x to the power 4 y. Okay, moving on to our next function, we can pretty much see here we have an outer and an inner function. We're going to find the derivative of cotangent of e to the power 2x. We actually have a couple of chain rules to do here. We see multiple sets of outer and inner functions. But first of all, we start with the derivative of cotangent, which we need to know is negative cosecant squared of x. Remember, x in this case is just still that inner function. So we found derivative of the outside function. Now we're going to take then we're going to multiply this by derivative of the inside function, which is e to the power 2x, which has its own inside function that we're going to have to multiply by the derivative by, which is 2. And now we're just going to move the 2 to the front, get rid of these signs, and this is the final answer, which matches answer choice B. Okay, so just doing these multiple sets of chain rules, very important to be able to identify our outside and inner functions that we have once again here. Okay, notice outside function is to the power 4, so we're just going to do that first. We have 4 cosine to the power 3 of x, and then we're going to take the derivative of the inner function, which is cosine. Derivative of cosine is negative sine, so we're going to multiply by negative sine of x. So the final answer that matches this is answer choice C, and that is the correct one here. Okay, moving on to the next. Going to let g be the inverse function of h. Notice that h of 2 is equal to 5. We just need to know the notation of our inside functions of our inverse functions. Whenever we take the derivative of an inverse function of x, it is simply equal to 1 over the derivative of f, parentheses, f negative 1 of x, like this. So our first job is to find, okay, what is our inverse function? Our inverse function is g. So when g is equal, so that means g of 5 is equal to 2. So that means our inner part here is 2, and then we just evaluate. Well, it's easier to just assign some values. We know that g is our inverse function, so this part is right here. So this is just the same as g of the derivative of g of 5 is equal to 1 over our regular function, which is just h in this case. So we're going to find the derivative of h of our inverse function of x, g of 5. As we can see here, g of 5 is just equal to 2 because it inverses the h. If h of 2 is equal to 5, g of 5 is equal to 2 because they're inverses. Now we just find the derivative of h at 2. Okay, derivative of h, we have 3 over 4 x to the power of 2 plus 2. We're going to substitute in 2 here. 2 squared is 4. We get 3 for this part plus 2. 3 plus 2 is 5. So then we take 1 over 5, and that is the answer here. Just 1 over 5. All right, on to the next. Is this a composite function? Do we have an outside and an inner function? In this case, we do not. We can see here that we are just composite. Well, no, we're not composite. We are just doing product rule here. So f is not a composite function. We do not have outside and inner functions. We have two separate functions, a trigonometric and a linear function, multiplying with each other. Okay, on to the next. We're going to find the derivative of this logarithm. Remember how derivatives of logarithms work. We are left with x ln of a, whenever we take the derivative of a logarithm, where a is just the base, and we know the regular log, the base is always going to be 10. Okay, so x is going to go out here. So that means we're going to put x squared minus 1 out here, ln natural log of 10. And then we still have to do chain rule here. We need to multiply by the derivative of the inner function. The derivative of this is just 2x, so our numerator is going to be 2x. Denominator is that. A is the correct answer here. All right, on to the next question. Where how can we rewrite this so it can be differentiated with the power rule? We're just going to FOIL out. It's the easiest way possible. That is equal to c. Just knowing these algebra rules, quite important. Okay. On to the next question, we're just going to find the hidden derivative here. The hidden derivative, we know we have the function for sine of x, and then we're trying to just evaluate this as x at x is equal to pi over 2. So we can just take the derivative of this. This is just 4 cosine of x and evaluate at pi over 2. Cosine of pi over 2 is equal to 0. So this function, 4 times 0, is still 0 regardless. All right, so A is the correct answer here. Moving on to our next question here, we have an inverse trigonometric function here that we're trying to find the derivative of. The derivative of sine is 1 over the square root of 1 minus the inner function squared times the derivative of the inner function, which is just 1/6 for this case. So we're going to multiply our answer with 1/6. At x is equal to 4, we're going to replace a u with x over 6. X over 6 squared is x squared over 36. So we have minus x squared over 36. Let's simplify this when x is equal to 4. Okay, when x is equal to 4, we have 1 minus 16 over 36. Let's first simplify this fraction, which is 8 over 18, which is 4 over 9. So we have 1 minus 4 over 9, which is 5 over 9. So now we have 1 over 6 times 1 over the square root of 5 over the square root of 9. Square root of 9 is 3. So we have the square root of 5 over 3. This reciprocates into 3 over square root of 5 times 1 over 6. And now we have the 6 here. We can rationalize the denominator, so we get that 5. So our denominator becomes 30. Our numerator becomes 3 times square root of 5. Then we can simplify to square root of 5 over 10. And that is our answer. Square root of 5 divided by 10. And moving on to our next question, we can see here that we're trying to find the derivative of this function. It is a quotient, so they're going to have to use a quotient rule. Let's see if they do it correctly here. All right, low. Okay, low function times derivative of the high function minus high function times derivative of the low function. Good. Let's see if they do it correctly with the derivative. These derivatives are correct. Putting it all together, let's see. We go from here to cosine that. And then they factor out x to the power of 7 from each terms. I believe this is correct. Yep, all of this is correct. All right. And that is our final question for this unit test. If you have any other questions regarding these more complex derivatives, you can leave it in the comments, and I will be sure to get to that very soon. We'll be starting Unit 4 soon enough, and I will see you guys with our continued study as we work our way through AP Calculus BC. I'll see you guys then. Goodbye.